Hi all. Hope I'm audible.
Yes, you are.
Yeah. Okay. So thanks, Natira. Thanks for that great introduction, and also thanks WiDS Sri Lanka for having me and giving me this great opportunity to present in this workshop. So yeah, let's jump into the session. So let me first share my collab notebook, and I hope all of you also have this collab notebook with you guys. Okay. So yeah, so today I'm doing this session. I'm giving some hands-on experience for you guys to handling a Kaggle data set. So this is basically for you guys to practice practice some Kaggle data set analyzing, or data analyzing using Kaggle data analyzing for a Kaggle competition before you moving on to your data set challenge. So yeah. So this is for you to get some practice for your datathon challenge before you move into your actual datathon challenge. So here I'll be doing a Kaggle data set, which is about this Delhi weather data prediction. So I hope you guys can check on this Kaggle page about this Delhi weather data, and then you guys can uh, hope you guys can download this data from this page. So you can find the link on the collab as well. And I hope everyone has this collab with you, and you guys can also code, or you guys can also try at the same time that I do this session with you. So yeah, let's start it off. So let me give a small introduction to the daily weather data. So same as your actual datathon challenge, this is also a weather data prediction or a forecasting, we can say. So this also got some um, uh, explanatory variables, as well as our time series forecasting measurement called temperature. So this is about some weather data in Delhi. So you can briefly read on this page and have some understanding about data as well. So, and here in the first section, I have included some important libraries that I'll be using throughout this workshop or this session. So you can import them for your collab first. So I have already done this. And then what we have to do is we have to load the data from our local environment. For that, you guys have to first download the data from this page and take it, save it in whatever the folder you prefer in your local environment. And then you have to upload it to the collab environment. I hope this was done in our morning sessions as well. And since this is taking a little bit of time to upload into the collab, I have already done this step. So, but if any of you don't have any idea about how to run this step, and how to choose the file and upload it, please mention it in the chat box. I'm happy to redo this step. So yeah, so then what we do is we basically read the data set, we read the CSV file, and then first of all, we check how much data we have in our hand. So then we can see we have 100,000 plus observations, as well as we have like 20 columns with some sort of data related to the weather. So let's see first how our data set looks like. So if we print the data.head, we can see how our data looks like. We have this date column, obviously, and then in the middle, we can see this temperature column, which is our target variable, and this is what we are going to focus. And also we can see some other columns like conditions, dew point, fog, hail, some other columns or some other information relevant to temperature predictions. So before moving on to the data cleaning part, I want to give you some information about my how I'm the direction that I'm planning to take this workshop or this session. So since in the morning sessions, you guys have covered a lot of data cleaning, data pre-processing, as well as the some data modeling with regard to the regression or the data or the time series prediction side as well. in my workshop, I'm not repeating the time series regression part or the prediction part. I'll be taking the time series forecasting direction. So you can see when I'm doing the data cleaning part, I'll be dropping the other exponential variables here, and I'll be taking a time series forecasting part. But you guys are encouraged to apply the things that you have learned from the morning sessions that we have done already. So you guys are encouraged to apply any techniques that you guys have learned, the time series regressions, predictions, whatever the techniques that we have given to you, that we have done in the morning sessions. You guys are encouraged to use it here, and you guys analyze this data set the way you want. But here in this workshop, I'll be taking a time series forecasting direction. So first of all, first thing first, the data cleaning. The data cleaning is really important when you're analyzing any sort of data in any sort of data science project, because as it says, garbage in, garbage out. No matter how you do your modeling, what deep learning model you use, what fancy model you use, what type of hyperparameter tuning you do, if you input any any unstructured data, like unclean data, you will end up with a very bad model or bad predictions. So first thing first, you have to go with the data cleaning. So first of all, we need to identify the data types we have, and we need to make sure that our data, like for the information, are in a correct data type. So here we can see our date time column, it's an object column. So in order to do a time series forecasting, we need to convert this into a time index, in a time series index form. So first of all, we need to do some transformations to the columns. Before moving on to that step, I want to restructure some of my column names, because you can see like it's in a very inconvenient structure in this data set, like with the prefix of this underscore and all. So what I'm doing is I'm restructuring my column names here. For my convenience, actually, that is. But make sure to read your rules and regulations in your datathon challenge, and make sure whether there's any restrictions of adjusting column names in your datathon challenge, because here what I'm doing is for my convenience, but make sure when you're analyzing the actual datathon challenge, you adhere to all the rules and regulations. So then what I'm doing is I'm converting my date time column to a proper format for proper date time index, and I have assigned it to my index. So then, as I said, I'll be taking a time series forecasting approach here. So I'll be taking only the temperature column here. So then finally, we can have a look at our data. So this is my final data, or my final data set looks like. So I have my date time index, and as well as I have my temperature column. So
Beshani, interrupting you for a moment. Looks like there's a problem with access for your collab notebook. So
okay.
I'll be copying the. Will you be able to go to your collab notebook? And I uploaded a copy actually, but I have. I'm a little confused as to why it doesn't show the option to share. So wait, let me so let me download it and send the file across on the Teams chat. So I think that would do.
Or else shall I send the link, like this collab link, like whether they can access it, like whether they will get the same.
Can you share it?
Yeah.
Yes. With everyone with the link can view.
Just try this link and let me know whether you will still get that access issue. And
Okay. I think that, yes.
yeah.
Anyone with the link. Yes. I think that will do. Okay.
Yeah.
Thank you, Beshani, and sorry for the interruption. And everybody who's following the session, can you please check the link that Beshani sent just now and get back to us whether you can actually see the codes?
Yes. If one of the participants can confirm this, it would be great. I think people can access it now. I got so yeah. I hope I can continue. So sorry for that inconvenience, guys. So you can carry out from this step onwards, or you guys can always see what I've done before as well. So yeah, moving on, guys. So this is my final data set. I have this date time index column as well as the temperature column. And then I want to check my null values, because with null values, we can't move forward in our data analysis. And here I can see I have 673 null values in my data. So as you guys can remember, I have 100,000 plus data individual observations in my data. So as a percentage, this null value is very small. If you take a percentage of these null values based on the for the number of observations we have, this is a very small percentage. But yet we can't go and directly remove these 673 null values without exploring the story behind of these null values. You can't do any operation, or just removing the null values, or just imputing it with several ways. You can't do any operations, or it's like it's recommended to not to do any operations without exploring the story behind the null values, because sometimes these null values give some important information that you might need to interpret your data. So it is always recommended to analyze your null values, or to visually, or whatever with the statistical methods or statistical testings, analyze your null values, identify the story behind your null values, and then do the relevant operation that you want to eliminate these null values. So at this stage, I will not be doing any operations to remove or to handle the null values. So I'm moving forward to data visualization section, and we'll see what's happening with these null values and what is the reason for these null values to be occurred. So hope you are clear with the data cleaning part. So I'll be doing some more data cleaning going on after the data visualization as well, because in any data science project, 80% is allocated for data cleaning. So data cleaning is really important, and that will really matters for your model predictions. So sometimes you will get bad prediction, not because the model not because that you have used the wrong model, because of that you have not cleaned your data properly. So yeah, with that information, let's move on to the section 2.3, which is the data visualization. So in Python, you have several libraries that you can do data visualization. So here I have listed down the most common data visualization libraries which we use day-to-day life with data analysis projects. So Matplotlib, Seaborn, and Plotly. Some people might not be very familiar with this Plotly library. So I encourage them to, I have included some references links. So I encourage them to go and refer what Plotly is. So basically, like if I summarize what Plotly is, like Plotly is a very interactive level visualization. Other than Matplotlib and Seaborn, the speciality of Plotly is you can do interactive visualizations with Plotly. So in this workshop, what I'll be doing is I'll be using all three libraries for you guys to get familiar how each libraries represent the data or the visualized data. So so first thing, I'll be doing this time series visualizations with Plotly. So since I want to use this time series visualizations more than once in this workshop, I have created a definition here with all the namings, column namings, and titles. So I have put some variables for them to define, and I've created a definition for it. So you guys can refer to this, and so this is very understandable, I hope, for anyone with the basic Python knowledge. And the special thing here is that I want to mention is like in Plotly, especially when you are using in the collab environment, Jupyter Notebook or Google Colab environment, you have to you can't just use figure.show to visualize your particular chart. You have to include what renderer like you are visualizing it. Otherwise, it will not be correctly visualized in the Colab environment. So this step is very important in Plotly when you are using it in the Colab environment or Jupyter Notebook environment. So yeah, hope that's clear. So first thing first, let's visualize our time series data. So let's see what's happening or what our data looks like. So we have seen from our data, like we have some sort of a hourly data data structure, and but that hourly data is also are like not consistent data we had. So it looks like this. So with the daily data, daily data, I can see some sort of inappropriateness during this period, which is in 2000, the year 2000. So as I said, Plotly is very interactive. What you want to, if you want to see something, like you want to make this clear, what you can do is you can actually maximize your chart and see exactly what's happening there. So like this, you can see what's happening. So you can see that most of the null values are, seems like most of our null values are occurring in this period. So that information we can see with this plot. So yeah, so we can note that information from this plot. So having that in mind, I'm trying to do some summarization for my time series data to identify some interesting pattern in my temperature data. So I'll be doing some hourly mean calculations, monthly mean calculations, and yearly mean calculation, and see what's happening in my data, and to identify some story behind of my data. So as I said before as well, it's really important to identify the story behind your data in order to give a proper interpretation. Not only the predictions, we need to give a proper interpretation sometimes. So it's really essential to identify your data and the story behind your data. So first of all, here I have visualized the hourly temperature mean, like how my data, or how this daily weather data fluctuate during a particular day in an hourly sense. So you can see that during the daytime, our temperature rising, and towards the evening and morning time, it's gradually reducing. So if we take the monthly means, if we plot the monthly means in a similar sense, you can see during so here in the x-axis it's months, 1 2 3 4 5 6 denotes the 12 months in the year. And you can see during the March July period it rises. The weather in Delhi, or the temperature in Delhi rises during the March July period. So we can call it as, in summer season it rises, and then you can see it's gradually decreasing towards the winter season or the December season. And if you check for the yearly data in a similar way, yeah, and you can see, we can see like our data varied from 1996 to 2017. In that period, you can see during 1999 there is a huge spike in temperature, and then it gets moved out after like 2000. It's moved out up until like 2015, and then again we can see a similar spike in 2006. So there can be something happening in Delhi to get this kind of a temperature structure. So you can see and you can explore some story from these type of visualizations. So yeah, I hope that part is also clear, like how you extract some sort of a story from data visualizations. So then the next important thing when you're analyzing the time series data is, like, you need to see like how resampling work, like how your data looks like when you resampling it in several different time periods. So here I have done hourly data resampling, daily data resampling, monthly data, and of course the yearly data as well. So you guys can visualize this separately, but I'll be showing you how it looks like in terms of hourly, daily, and monthly. So if we first take this hourly data resampling, yeah. Um, Yeah. So in the hourly data resampling, you can see our data is really inconsistent. Even though we have seen some hourly pattern in our Delhi weather data initially, we can see once we convert it to a proper hourly resampling structure, we can see a lot of null values in our data. So with hourly data, we can't do this prediction, or we can't do this forecasting. So let's go one step forward. So let's go to the daily data visualization. So our data has been smoothed out a little bit, and now you can clearly see that lag of null values here in the during the data 2000 during the period of 2000 and 2001. So similarly, if we show the monthly one as well, yeah, you can again see that you can again clearly see that lag in the data between 2000 and 2001, and also you can see a nice seasonality pattern in monthly data. So with this I can get some conclusions. So since I have a lot of data here in this data set, that's also I have to mention, otherwise you can't sometimes go for resampling methodologies if you do not have lots of data in your data set. Since I have lots of data in my data set, I'll be going ahead with the monthly data resampling, and I'll be forecasting monthly temperature here. And also, since I have seen a lot of missing values here before the 2001 period, moving on, I'll be dropping any data before 2001, and I'll be going ahead only with the data after 2001. So in 2.4 section onwards, you can see that I'll be analyzing monthly data. And first of all, I'll be dropping any data before 2001. So then I'll again visualize it. Now you can see a very smooth time series data here, and we can't see any noticeable null values here as well. So if I just show you my data now, it's in monthly structure. So you can see my date time index has changed here. So it's from month to month from 2001 onwards. And now what I'm going to do is, now I'm going to check my null values again. So if you just check your null values again in your monthly data, now you can see you have 0 null values. So if we remove those 673 null values before, like at the very beginning in our daily data, we might lost some information. So but since we had like a lot of data here, we what we have done is we have started analyzing data from 2001 onwards. But in another situation, like where you do not have such amount of data, what you can do is you can go for a imputation, mean imputation, mode imputation, or whatever the imputation that is relevant with your data, that match with your data, you can use. Or there are so many other things that you can do with null values. In time series context, some people might replace the temperature data, mostly when it is in daily data structure, they will replace it with the day before temperature as well. So any sort of null value replacement you can do if you have very small data set. But in this case, since we have a lot of data, we have dropped the observations before 2001. So yeah. So I hope you guys are clear up to now. If you have any questions, please send it to the chat box. I'm very happy to answer them as well. Okay, moving on. So we'll do a little bit of more EDA as well before we moving on to our exact modeling. So since we have now monthly time series data in our hand, usually when you're analyzing time series data, it is really important to identify time series components within the data. So identifying or separating out time series component within the data, that process we known as decomposition. So you can go ahead and what decomposition mean and what time series component means if you do not have much understanding about these terminologies. But here I have included, there are 3 basic time series components: trend, seasonality, residual. Trend means general movement over the time, and the seasonal mean the special behavioral structure captured in individual seasonal period. It can be like quarterly, monthly, yearly, whatever the structures that you might see in your data. And the residual. So residuals means everything that is not captured by the trend and seasonal is going to the residual part, the remaining part, or the error term. So these are the 3 main components in time series, and each of these components sometimes will give you some information that can be addressed during your data preparations and model selection phases. So, and also when you are doing this, when you're identifying these time series components, there are 2 techniques. One is additive time series, and the other one is the multiplicative time series. time series. So we usually identify these two variations in our time series, like additive structure and the multiplicative structure. If the magnitude of the seasonal component or trend component changes, if the magnitude changes over the time, we usually identify those time series as multiplicative. Otherwise, if the magnitude stays constant over the time, the magnitude of the seasonal component stays constant over the time, we identify them as the additive structure. So here I have included some links for you to go and get some more theoretical understanding about these components as well. So you guys are welcome to go and get more knowledge on these aspects. So in Python, let's now do this decomposition and see how our data looks like and what special characteristics within this data, or what special components we have in this data. So for that, we have the seasonal decompose package library, this function in our in Python. So you can use that. You can use your monthly data. And since I feel like from this visualization, since I can't see much of a variation in our seasonal component, it looks like it's constant over the long period. So here I have used the additive structure, but you can change it depending on the data that you have and the visualizations that you see in these kind of visualizations that you see. So here, once you do the decomposition, it will give you how the trend looks like, how the trend in our data looks like, how the seasonality looks like, and how the residual looks like. So you can see there's a proper seasonality in our data, so that is identifiable. And then you can see some sort of a trend in our data, and as well as you can see our residual plots, like it's here and there. And sometimes it's not like that we have any other components, like any other patterns in our residual. It seems like it is random, but let's see in the modeling phase how it looks like after the model as well. So yeah, hope you are clear with the seasonal decomposition. And then we are moving on to this stationarity, and why this stationarity is important. And since we have observed this seasonality that is exhibits in our data, and also a little bit of trend, this can be effect for our time series at different times. So why this stationarity is important? Because a lot of statistical testing, statistical modeling, even some machine learning modelings are depend on this stationarity assumption of data in time when it is come to time series. So what is this stationarity? Stationarity means data whose properties does not depend on time. That means if the mean and variance remains constant with the change in time, and it is not depend on the time component, we will identify them as stationary data. And if our data is not stationary, it is recommended to convert your data into a stationary structure before doing any modeling. So let's see what are the ways of checking this stationary. There are two ways of checking the stationary. One is the visualization way. The other one is a statistical test called augmented Dickey-Fuller test. So we'll see how both will work with our data. So first of all, I'm planning to do the visualization thing and identify stationarity with the visualization. So when it is come to identifying stationarity with visualization, what we use is this rolling mean and rolling standard deviation. Or you might have heard this as moving averages or moving standard deviation. So let's first plot the data. So you can see, so we mainly do this. So what is rolling mean and what is rolling standardization mean? It is simply, if I explain it in the mean, the rolling mean is simply the average of the last n value. So here I have used the Windows 6. It's the average of the 6 months period. Even averaging those, even if we average our data in a particular period, if we can see some sort of structure, then it says that our data is not stationary. So this is how we visually identify the stationarity. You can plot your rolling mean and rolling standard deviation with your original time series, and then even in that series, if you see any patterns in rolling mean and rolling standardization, that means that our data is not stationary. And let me adjust this and put 12 months, because I doubt with the visualizations that we have done, we have this 12-month sort of seasonality. Let's see whether it will get adjusted if we roll in 12 months. So you can see now those pattern is not visualized in 12 months window. So that means doing a 12 months rolling adjustment means like it has got smoothed out. So let's see with the Dickey-Fuller test as well how it works. But now we sort of have an understanding with the visualization. We can see that our data is not stationary, but with the 12 months window, it got some sort of stationary. So yeah, and this is how we visually check the stationary. Now let's move on to the statistical test of this augmented Dickey-Fuller test, how to quantify this stationary and how to get a quantitative idea about whether our model is or our data is stationary or not. So for that purpose, we use this augmented Dickey-Fuller test. This is a hypothesis testing which identifies the stationarity of the data or the stationarity of a time series data. And null hypothesis is there is a unit root, or it says that the time series is not stationary. Alternative hypothesis is that the time series is stationary. So if I also for this purpose also, since I'm going to use this again and again, I have created the definition for my convenience. You can run this definition and you can check the stationarity of our data before any adjustment. So you can see the p-value is 0.56 and that is greater than 5. If we take the 5% significant level, so that is greater than 0.05, where that we are not rejecting our null hypothesis. That means our data or our time series data is not stationary, right? So even the Dickey-Fuller test suggests that our data is not stationary. So now we visually saw that our data is not stationary. Dickey-Fuller test suggests that it's not stationary. Now let's see how we are going to adjust or how we are going to transform our data to be non-stationary. So again, there are different ways of doing this process or transforming it to a non-stationary data. But here I'll be doing the differencing, and even in the differencing techniques, I'll be using seasonal differencing method because I have seen a proper seasonality structure in my data. So differencing is a method of transforming a time series data set, and it will remove the dependencies on time. Like the temporal dependencies on time, it will remove by differencing. Again, you can search the theoretical aspect of this differencing as well, if you're keen on learning on those terminologies. So here I'm using the seasonal differencing, and I'm using the 12-month seasonal differencing because we have visually also we have seen that it's got adjusted with the 12 months rolling, and since it's like visually clear that we have a 12-month seasonal pattern, so I am using 12 months difference in here. So this is how it looks like once you do the differencing for your data. And then what I'm going to do is I'm again checking my I'm again applying my augmented Dickey-Fuller test to check whether now it is got stationary or not. So again, I'm applying my augmented Dickey-Fuller test. Now you can see, if you check the p-value here, it is less than 0.05, which suggests that we reject H0. That it's reject H0. That means we are accepting the null hypothesis, which says it is stationary, right? So yeah, I hope you are clear up to this, and you can see on if you want, you can plot your difference series as well. Now you can see it is more random, and you can't see that seasonality structure. You can see some here and there, some spikes, but you can't see a proper seasonality structure here after the differencing. So yeah, I hope that concept is also clear for you. And then we'll be moving forward to another two important theories before we model. That is, autocorrelation plots and the partial autocorrelation plots. So what is this autocorrelation plots and what is this partial autocorrelation plots? And I'll be giving some understanding about where we use them. So autocorrelation is the correlation between a time series with its lag version itself. So when we are starting, usually we start the ACF plot in lag 0. That means the correlation of time series with itself, and from lag 1 upwards, it will give the correlation of time series with its lagged version of itself. So we mainly use this ACF plot to identify which model that we usually use for our data, as well as to specially to identify the MA terms, the moving average terms that we want to use in our time series model. So for those who don't know these moving average models, the moving average models assumes that your time series depend on the error terms, and this is the equation of the moving average terms. And again, I encourage you guys to search these terminologies if you do not have much statistical understanding of them. So if you plot the ACF, you can see that it has this decaying pattern, but the values are tapering like from positive and negative. It has this decaying pattern, and you can see like we usually ignore this lag 0, and from lag 1 it is significant, and it's some kind of suggesting that we should use the MA1 model, but let's see with the hyperparameter tuning as well. And also you can clearly see the seasonality, and in this 12-month period it has a significant component has been shown in the autocorrelation plot. So these kind of identifications we can do with the ACF plot. And then what is PACF? PACF, or the partial autocorrelation, is that it captures the correlation between two variables after controlling the effect of the other variables. It's a partial correlation which eliminate the effect of the other variables when you are calculating the correlation between two variables. So again, I suggest to go and check the theoretical aspects of this. So PACF plot mostly used to identify the autoregressive terms or the AR terms of the time series model. AR model, or the autoregressive model, is that it assumes since like in the MA models, it assumes that it's depends on the error terms. In the AR model, it assumes that the time series depend on its lag terms. So this is specifically we use for identify the AR term. So if you check on the plots, partial autocorrelation plots, you can identify the AR terms with the significance spike in the PACF plots. So yeah, so with this, we are finalizing the EDAs of the time series, and we got a lot of information. We have put a lot of information to a basket, which will be needed in selecting our model, as well as when it is come to the hyperparameter tuning and when analyzing our data. So now from section 3 onwards, we will be doing the modeling part. So in the section 3, what I have used here is the SARIMA model. SARIMA model is seasonal autoregressive integrated moving average model. So it's also we known it as like seasonal ARIMA model. So why I thought of applying this SARIMA model for this particular data? This is because that we have seen a clear seasonality in our data. So ARIMA model will not be enough for our data. So we have to do something to control our seasonality. So that is why I've used SARIMA model here. I've picked the SARIMA model here. And also, even though I have not used any exogenous variables or any other independent variables for time series prediction, as I said earlier, if you are keen on applying if you are keen on doing the same analysis with the exogenous variables or some independent variables, I suggest you to use SARIMAX model. You can note down it, and you can search what is SARIMAX model. It's a model that we use with the time series regression plus time series forecasting for the residuals. I hope you guys have covered the time series regression part in the morning sessions. So it will be easy for you guys to take the knowledge of SARIMAX model as well. So yeah, that's a small tip if you are planning to analyze your data with exogenous variables as well. So yeah, here I have used here I have thought of moving ahead with the SARIMA model, and this is how this is the structure of the SARIMA model. Here we have the ARIMA components, the P value, difference in value, and the Q value. That means AR terms, difference in values, and MA term, as well as we have the seasonal component, and also we need to specify the seasonal. Here we need to specify the seasonal seasonality period as well, the S, right? So before we moving on in applying any model, what we want to do is data splitting, because we need to validate our data. We model our data only for some part of the data, the training set, and then we should separate out some data, and we should not inject that to our modeling phase, and we need to see our performance of our model to an unseen data. So that's why we do this data splitting, train and test. So here I have split my data. I include the scenes, and also when you're splitting time series data, it is really important to you to satisfy with the the order of the data, because this is not the cross-sectional data, these are time series data. So please aware about the order of the data. You can't do any randomized data splitting when it is come to the time series, unlike in the cross-sectional data. So here I have used data up to 2014 to train, and the data from 2015, the 2 years data for my testing. But when you're analyzing the original data challenge, again, read your rules and regulations and see whether you have any specific rules and regulations applied when splitting the data. Or in the Soumya session, I have seen that she has covered that in the Kaggle competition, they have separately given the train set and the test set. So for you, you might not need to do the train and test on your own. You have to use their train and test samples. Otherwise, you might get rejected when you submit the predictions. So yeah, so this is how my trains looks like. It's up to 2014 December, and this is how my test looks like. It is up to it is from 2015 to 2017, right? Yeah, I hope that data splitting part is also clear. And then we'll moving on to hyperparameter tuning. So first of all, let me give a small understanding about what is hyperparameter. What are hyperparameters? These are the parameters to identify the model architecture. And why this hyperparameter tuning is essential, like we need to identify the parameters which will give the optimal model architecture. So that is why we always go with the, whenever we are doing this whenever we are doing the data analysis, it is important to identify the optimal model architecture. So that is why we are using this hyperparameter tuning. So whenever we do this hyperparameter tuning, especially in the time series context, so this AIC or Akaike information criteria is something that you usually see, and this is a model performance evaluation metrics, I would say. AIC is a performance evaluation metrics. Or it is like it's a metrics that identify the quality of the statistical model. So the AIC value is the one that we use to identify the optimal parameters, or the optimal model, optimal parameters which gives us the best model. So that is why I included the AIC value here, and so some sort of theoretical understanding of AIC here as well. So yeah, again, I have created some definitions to do this hyperparameter tuning. So in this case, I'll be doing in hyperparameter tuning from my own sort of a definition. But now in machine learning, you guys have plenty of libraries to do this hyperparameter tuning, grid search, randomized grid search. So there are so many other libraries that you can do this automatically. So in sklearn, basically, you can go ahead and check on those libraries as well. But in this case, I have created this, I have manually created this definition for this purpose. So yeah, here I run my definition, and I'll be giving my parameters in a way that it should assign to the I first identify some ranges that I should give to my parameters. So I vary my PDQ value from 0 to 2, and similar to the PDQ value of seasonal parameters, I'm arranging them in a similar structure. So first of all, I'm arranging them, and then I'm connecting them with my definition. So then you can see it takes some time to run this for the given for loops. What it does is it's run the model for the each parameter combinations that we have assigned. It run the model and for the each parameter combinations that we have assigned, and it will give the Akaike information value for the each model, and it will select the best model with the lowest Akaike information value. So how we select the best model with the Akaike information value is that if the model that offers the lowest AIC is the best fit. So I have ordered this results data frame in a way that it will get the lowest one on the top, like in the ascending order. So you can see this is the model that it has given the lowest Akaike information value. So then what we do is we go ahead with these hyperparameters to fit our best model. So this is how I have proceeded with our hyperparameter tuning for the SARIMA model. Then what I'm going to do is with those hyperparameters that I've received, I'm going to fit my best model. And then you can see the model summary here. So here you can see again the Akaike information values and some other statistics that you can see to identify whether our residuals, whether the assumptions are satisfied. And also you can see all the parameters are significant, or the coefficients are significant in this model. So that is also a positive sign that this model is a good model. So then what I'm going to do is, it is essential to check the assumptions once you fit the data. So in SARIMA model, the main assumption is that residual should follow a normal distribution. So here that will so here in the StudyMax package, that they will give these plot diagnostic functions to identify you several, like it's plot several diagrams for you to identify whether our residuals are normally distributed or not. So this normal QQ plot, you can see like it's the data has been arranged in a 45-degree angle and it is not scattered much. So from that we can assume that data is following, or our residuals are following sort of a normal distribution, and residuals are like randoms and no other components has been transformed to the residual. Like we don't want to separately analyze residual also to extract any other components that has been gone to the residual. So this is how we do the model assumption check. And then what we want to do is we need to get the prediction data for the test set. For whenever you want to get the prediction data, you need to give the lengths of your trained data and the test data, and you have to define from when and where you want to predict here in this package. So I'm going to run this line as well, and then I'm going to generate my prediction values with their and also I'm going to generate their confidence intervals here, because that opportunity was given as a function in this StudyMax package, that you can get not only the prediction values, you can get a confidence interval for your prediction values. So then as the model performance, I have used the RMSC value. So this is the same model performance metrics I think that you guys have to use in the Datathon challenge as well. So I'm using this as well. So it's 1.7, pretty much a good model. And what you can do is you can plot this and see as well how this goes. Yeah, here I'm plotting my predictions along with all the data. So you can see this blue line is my trained data, and this orange line is my test data, and this green line is my predicted data. So you can see that it's going very similar with my test data, and my RMSE value is also pretty good value. So yeah, so with this, I think I have covered from A to Z how you can do a SARIMA model with the time series forecasting. And also I'm remembering again, like if you want to do this the same thing, you can the same analysis with exogenous variables or the independent variables. The similar package offers you, the SARIMAX package offer you that opportunity as well. But before that, I encourage you to take the knowledge and also combine the knowledge you got from the morning session to identify how to do the regression predictions along with regression predictions for time series data, and then read about a little bit of SARIMAX model as well. So then you can apply it with the exogenous variables as well. Hope this is clear and this modeling phase is clear for everyone. If you have any questions, you can either ask it directly or you can put it into the chat box. And then again, I just want to give you a little bit of understanding about how you save your prediction files, because this is very important when it is come to the Kaggle competition. This was actually mentioned in Soumya's presentation as well, but I want to give some hands-on experience on that as well. So if you just, sorry, if I just show my predicted values here. So if I just show you my predicted values here, it is not in the structure that Soumya has explained in her previous session. It has a time series index and the values. It has a time series in there and it has a values. But when you want to upload it to the Kaggle competition, you need to transform this prediction in a way that they have asked, or they have given they might have given the specific rules and regulations. So you need to first of all transform your data in a way that they have asked. But since this Delhi weather data is not an ongoing competition, they have not given any structure of uploading the data. But I am moving ahead with the example that Soumya took with her in her session. So here what I have done is I have transformed my prediction data set, and then I have assigned this exact same column names that they have asked me to put. So this is where I am including the exact same column names, and if I just print it, you can see I'm following the exact same column names and exact same structure that they have given. And whenever you want to whenever you want to save it to your local from the collab, you can use this. The files library give you that opportunity of downloading this CSV file to your local environment. So once you do this, it will get downloaded. Right. So if you just see this prediction file, it follows the same structure like this. So this is also to give you a little bit of understanding what Soumya has explained in terms of uploading the Kaggle dataset to the competition. So yeah, so I hope this section is also clear for you guys. And in the fourth section, I have applied another model for this data set, which is a deep learning model for long short-term memory. But I'm not going very deep into this model because we have a very limited time. I think I am very close to finish my session. So to get my the allocated time. But I'll give you a brief understanding about how this model works and how I apply this, but I'm not going to very deep into this. But again, I'm encourage you to try these models as well. The purpose of this workshop is to give you a more understanding about different model techniques. So that's why I included this part as well. So you guys can do a self-study on this. So LSTM, or the long short-term memory, is a deep learning model of handling a time series forecasting. So this is coming from, so this is the parent, if I said the parent, parent of this LSTM is the RNN, which is a recurrent neural network. LSTM is also a recurrent variety of a recurrent neural network, but this has a very important feature which it can learn long-term dependencies of data. And also some issue of these neural networks are, even though these neural networks are developed to to be similar to the human nature, but the disadvantage of a neural network is that it has this vanishing gradient issue, or else, if I say it in another word, it has this loss of information issue. But this LSTM has improved to eliminate that issue, which what it does is, like, it identifies the, like, whenever the same connections reoccur over a long period of time, this loss of information issue can happen. But in LSTM, what it does is it ignores the useless data, and it takes only the useful data when it is reading the data. So that is the main importance or the main advantage of LSTM. So in LSTM, you can use, there's a thing called this time steps. When you define the time step, it will go to that particular step, and it will read the data in a way that it will ignore the useless information. And in some tutorials, you might see that these time steps might be defined as the forget gate as well. So as its name suggests, it will, it name suggests that it ignore the useless data in the process. So again, I encourage you to go and get some more theoretical understanding about these deep learning methodologies without blindly coding them. And in the data preparation section, what you have to do is, before you go into any deep learning model, you have to do some scheme my data. And also LS team expect your data input to have some sort of a structure, like, we have to give the samples, time steps, and the features. Like we have to give the input feature, forget steps, or the time steps, as well as the number of features. So you can manually reshape your data, as well as there is another library called this, or the function called this time series generator, which automatically do this job for you. So here I'm using the time series generator function. And also, since I have seen a clear 12-month seasonality in my data, I'm using the time step as 12. And then I'm doing a very simple LSTM model here. Of course, you guys can develop this. Of course, you guys can try different ways of, tuning this, like adding different hidden values, or combining LSTM with a CNN model as well, or like anyway, like you guys can do this hyperparameter tuning in a way you want, with the knowledge you have in your, with the knowledge you have with your data. So then here you can see my LSTM architecture. I have my input layer, I have my hidden layer, and my output layer is just a simple structure of the LSTM. And then you can print your model summary here. And I'm setting an early stopping for my LSTM, because it will stop once you define an early stopping for your deep learning model. It will allows to stop the training when the model performance stop improving. So for that, I have given an early stopping here with the patience of 50. But again, you can tune this in a way you want and try different modeling. And then I'm doing my model fit with the generator that I've done before. This will take a little bit of time. Yeah, and then what you can do is you can visualize your loss per epochs and how it looks like. And you can see, even though it is like a little messed up, you can see the loss is varying over time, but it decreases significantly, right? When the epoch size increases, it decreases significantly. And this is our epoch loss plot. And then what you can do is, since we have fit the model, you can get the test predictions out. But make sure we have reshaped our trained data before we put it into the put it into the LSTM model. So in a similar way, you need to transform your test set as well. But since we have used a automatical generator for transform the training data, here I'm using manual reshaping. So then you will get the both, you get the idea of the both ways. So I manually reshape my test predictions in a similar way that I reshape the train set and get the test predictions out. But then again, we need to do another transform, because because recall that we have normalized our data before we put into the model input data. So then we need to again retransform it whenever we got the prediction. So to identify the true predictions, we need to inverse our transform. So here I'm inversing my transform, and then I'm taking the true predictions. And then similar to what we have done with the Serima model, we can go ahead and identify the model performances with the RMSE model performance. So here you can see, since I did the very basics model, I'm getting a huge RMSE value 7.7, which is comparatively to the huge to the whatever we got for the Sarima model. But of course, you guys can do a lot of high parameter tuning and change this and try to improve this model or the RMSE values or prediction values. So again, you guys can check the plots as well. So you can see that it is not predicting as well, like as good as we saw in the Sarima model. But again, this is a deep learning model. So you guys can try different ways of improving with model hyperparameter tunings. And of course, I have used a very, very basic LSTM model with just input layer, hidden layer, and an output layer. So yeah, I hope you guys have got some sort of understanding about this deep learning model as well. And I'm very sorry that I wouldn't be able to go very deep into this side with the limited time that I got allocated. So with this information, my session is over, but you guys are very open to ask any questions that you have with regard to this data set, or you guys can ask any questions from Saumya. I hope Saumya is also in the meeting yet. So if you have any questions with regard to the Kaggle competition or this particular section that I've done, you're open to ask. And thank you very much for listening this session. I hope you have got some understanding about data analyzing with the Kaggle with the Kaggle data, and very good luck for all the teams who are participating for the WiDS Datathon Challenge. Thank you, guys.
Okay, thank you so much, Beshani, for the wonderful session. If you have any questions, you can ask now.
Hi.
Yes.
So I was told to ask this, plus I have this question myself. The mentor also wanted to know whether I will be participating individually or whether I will be assigned to another team. Because right now with my mentor, I'm the only person.
Yeah, so earlier we have 2 teams participating from this. Apart from that, the other most of them were individuals, and